Hello everyone and welcome back to the channel. Today we are diving into a fascinating aspect of solar energy, dye-sensitized solar cells, or DSSCs. And specifically, we are going to explore how tiny metallic nanoparticles are supercharging their efficiency. Let's start with something truly remarkable that happens at the nanoscale. When we talk about nanoparticles of metals, particularly ones like silver, we encounter a phenomenon called the surface plasmon. Hey wait, that's an elegant description. Imagine the free electrons on the very surface of these nanoparticles. When light of a very specific wavelength hit these nanoparticles, it's like striking a bell for these electrons. They don't just sit there, they start vibrating collectively, in unison, creating a powerful resonance. This collective vibration of free electrons is what we call the surface plasmon excitation. It's essentially the nanoparticles acting as a tiny, highly efficient antenna for light. And here is where it gets really exciting for solar cell technology. This incredible phenomenon, the surface plasmon excitation, has been cleverly utilized to significantly enhance the light absorbance of the dye that's so crucial for our dye-sensitized solar cells. Take this note. These DSSCs are often made with a porous thin film of titanium dioxide or TiO2, which acts as a scaffold to hold our light-absorbing dye. By strategically incorporating these metal nanoparticles near the dye, the plasmon resonance effectively acts as a localized amplifier, channeling more of the incoming light energy directly to the dye molecules, allowing them to capture more photons and generate more electricity. Now, before we delve deeper into the specifics of how these nanoparticles are integrated, let's quickly recap what a dye-sensitized solar cell actually is. The illustration. Unlike the solid-state silicon solar cells you might be more familiar with, a dye-sensitized solar cell is what we call a wet solar cell. It's typically composed of two conductive glass electrodes. Between these two conductive layers, we have an interim electrolyte solution, which acts as the charge transport medium. And critically, on one of these conductive glass electrodes, we have a film of titanium dioxide or TiO2, which is generously carrying our light-absorbing dye. This dye is the heart of the cell, responsible for capturing sunlight and initiating the electron flow, the current. So in a sense, we are taking this elegant bio-inspired design of the DSSC and we are giving it a boost with a cutting-edge nanotechnology. By harnessing the power of surface plasmons on metal nanoparticles, we are making our dyes even more efficient at capturing the sun's energy, pushing the boundaries of affordable and sustainable solar power. Stay tuned because in the next segment we'll explore the different types of metal nanoparticles used and the precise mechanisms by which they enhance DSSC performance. Let's get a bit more specific about the structure of our DSSC. One of our conductive glass plates isn't just plain glass, it's coated with a special titanium dioxide TiO2 film that's been sintered on. Think of sintering like creating a strong bond. This TiO2 film isn't solid, it's incredibly porous like a sponge, with countless tiny pores, often just tens of nanometers thick. This huge surface area is absolutely crucial because it's where our dye will attach. The other piece of conductive glass simply serves as the opposing electrode, completing our circuit. Why are DSSCs creating such a buzz? It boils down to two key factors: ease of production and impressive efficiency. Compared to traditional silicon solar cells, DSSCs are relatively straightforward and less energy intensive to manufacture, making them potentially much more economical. And despite this simpler production, they're surprisingly efficient. We've seen reported conversion efficiencies reaching around 11%, which is a fantastic figure for this type of cell. This combination of affordability and a strong performance means that dye-sensitized solar cells hold immense promise for the future of truly economical and highly efficient solar energy solutions. Now let's talk about the heart of the DSSC, the dye itself. For a long time, ruthenium complexes have been the gold standard for sensitizing dyes. Because they perform exceptionally well, efficiently adsorbing specifically onto the surface of that porous TiO2 film we just discussed. This precise attachment is key for effective electron transfer. However, there is a significant hurdle. While ruthenium dyes are great, their light absorption coefficient is inherently lower than traditional semiconductors like silicon. This means they don't capture as much light energy, which quiet simply hampers our effort to push efficiency higher. So the big question becomes, how do we make our light absorbing layer, that dye-coated TiO2 film, more effective? The answer is clear. If we significantly boost the light absorption coefficient of that TiO2 film carrying the dye, we directly pave the way for dramatically enhanced DSSC efficiency. This brings us to a crucial challenge and an exciting solution: enhancing the absorption coefficient of ruthenium dye itself, specifically the well-known this type of ruthenium 2 dye, by strategically incorporating silver nanoparticles. Our goal is to push the efficiency of ruthenium-based DSSCs beyond the typical 10% mark. Remember our ruthenium dye? It has characteristics absorption peaks at 400 and 535 nanometers, which is due to a process called metal-ligand charge transfer. It's at these wavelengths that the dye truly comes alive, absorbing light and generating the charge carriers that produce electricity. And our research directly supports this approach. As shown in this figure, which exhibits the absorption spectra of different silver dye films, we clearly observe that as the dye concentration increases, the absorption around 550 nanometers significantly rises. This demonstrates the powerful potential of optimizing dye concentration, especially in conjunction with plasmonic nanoparticles, to overcome the inherent absorption limitations of ruthenium dyes and unlock higher efficiencies in DSSCs. It's an exciting path forward in solar energy. Now let's look at some compelling data that truly highlights the impact of the silver nanoparticles. We compare the pure dye film to our silver dye films. This proves that the dye significantly increases its light absorbance with a silver nanoparticle. This isn't just a slight improvement. This decisively proves that the dye's ability to absorb light dramatically increases with the presence of silver nanoparticles. It's a clear win for boosting the performance of our dye-sensitized solar cells, allowing them to capture much more of the sun's energy.